2 days ago, 4 astronauts plunged through Earth's atmosphere and splashed down in the Pacific Ocean, marking a moment that hadn't occurred in more than half a century. Human beings had traveled to the moon and returned safely. Artemis II is complete. The Orion capsule now rests on the deck of the USS John P. Murtha, its scorched exterior telling the story of a high-speed encounter with Earth's atmosphere. Inside NASA facilities, engineers are already dissecting every inch of data, every sensor reading, every fragment of material. The crew, Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, are back in Houston, undergoing medical evaluations, answering questions, and reliving every second of the mission for teams that need to understand exactly what worked and what didn't. There is no pause, no extended celebration, no moment to catch their breath, because Artemis II was never the destination. It was the trigger. What happened on Splashdown Day wasn't just the conclusion of a mission. It was the beginning of one of the most aggressive, tightly scheduled, and technically complex space campaigns ever attempted. NASA is now staring down a timeline that demands it accomplish, in roughly 2 years, what previously took a decade of preparation during the Apollo era. And the stakes are even higher this time. The next phase of Artemis isn't just about going back to the moon. It's about staying there. Within a compressed window, NASA is planning 3 major milestones: a full-scale test of lunar landing systems in Earth orbit, a crewed landing near the moon's south pole for the first time since 1972, and the early construction of a permanent lunar base. All of this depends on hardware that in many cases has never carried a human being. The first and most immediate concern is something deceptively simple: the heat shield. When Orion returned during Artemis I in November 2022, its AVCOAT heat shield didn't behave exactly as expected. It protected the spacecraft. Internal temperatures remained within safe limits, but the external surface showed unusual wear patterns. Chunks of material had chipped away. There were cracks, pits, and irregular ablation marks that didn't align with computer simulations. Engineers were left with a troubling realization: their models were incomplete. For Artemis II, NASA adjusted the re-entry profile to minimize time spent in the temperature range that caused the most damage. They altered the skip re-entry trajectory, the maneuver where the capsule briefly bounces off the upper atmosphere before diving back in, to reduce thermal stress. It worked. The astronauts came home safely, but the problem didn't disappear. Initial inspections after splashdown revealed similar patterns: divots, cracking, uneven ablation. Not catastrophic, but not fully understood either. This is the kind of uncertainty that keeps engineers awake at night, because while the shield is performing its fundamental job, unpredictability is the enemy of certification, especially when lives are involved. The conditions Orion endured were extreme. Re-entering at approximately 25,000 miles per hour, the capsule slammed into Earth's atmosphere at Mach 33. Plasma formed around it, cutting off communications for several minutes. Temperatures outside reached nearly 5,000 degrees Fahrenheit. Inside, the crew experienced intense deceleration forces, approaching 4 times Earth's gravity. And yet everything functioned. Parachutes deployed precisely on schedule. Guidance systems held true. The landing zone was accurate to within miles after a journey of hundreds of thousands. The crew exited under their own power. From a mission standpoint, Artemis II was remarkably close to flawless. Over 10 days, Orion proved it could support human life beyond low Earth orbit. After launch on April 1st, The crew spent time in high Earth orbit testing systems before committing to translunar injection. 3 days later, they looped around the far side of the moon, reaching a distance that broke records set during Apollo 13. They saw something no human had ever directly witnessed: the far side of the moon in person, not as data, not as images from probes, but with their own eyes. Cratered landscapes stretched endlessly beneath them. Jagged terrain cast sharp shadows in the stark lunar light. It was a world both familiar and alien, mapped in detail, yet never truly experienced by humans until now. Then came an unexpected bonus. As Orion moved through its trajectory, the moon passed between the spacecraft and the sun, creating a total solar eclipse from deep space. For nearly an hour, the sun vanished behind the lunar disk, revealing a glowing corona stretching out into darkness. It was a sight no Apollo astronaut had ever witnessed in quite that way. Moments like that don't show up in mission plans, but they matter. Still, despite the success, challenges remain. Engineers are already working on improvements. The Orion service module requires design adjustments, including a valve redesign. Even the onboard toilet experienced issues, something that may sound trivial until you remember that 4 people were confined in a spacecraft the size of a large SUV for 10 days. These are the kinds of problems that must be solved before the next mission, because the timeline is unforgiving. NASA has roughly 15 months to prepare for Artemis II, but Artemis III is no longer what people expected. Originally, it was meant to be the grand return to the lunar surface, the mission that would place astronauts back on the moon for the first time since Apollo. That plan has changed. Now, Artemis III is a test. Instead of heading to the moon, the mission will remain in Earth orbit. Its objective is to validate the most complex and unproven elements of the entire program, the commercial lunar landers. For the first time, astronauts will rendezvous and dock with vehicles developed by private companies. SpaceX's Starship human landing system and Blue Origin's Blue Moon lander. These spacecraft will launch separately and meet Orion in orbit. The crew will transfer between vehicles, test systems, evaluate life support, and simulate the operations required for an actual lunar landing. It's a full dress rehearsal. The comparison often made is to Apollo 9, the mission that tested the lunar module in Earth orbit, before Apollo 11 made history. Apollo 9 doesn't get the same recognition, but without it, the moon landing wouldn't have been possible. Artemis III plays the same role, and it may be even more critical, because the systems being tested are far more complex than anything flown during Apollo. SpaceX's Starship HLS, for example, requires orbital refueling, an operation that has never been performed at this scale. Multiple tanker flights will need to deliver propellant to a depot in orbit. That fuel must then be transferred to the lander before it can proceed to the moon. Each step introduces risk. Each step must work. Blue Origin's approach is different, more traditional in some ways, but still unproven with crew. Both landers must complete successful, uncrewed demonstrations before astronauts are allowed on board. And even then, uncertainty remains, because the first time these systems operate in their final configuration may be during an actual mission with humans inside. If Artemis III succeeds, the path opens. If it doesn't, everything slips. Assuming success, Artemis IV becomes the moment the world has been waiting for: the return to the lunar surface. Planned for early 2028, the mission will send 4 astronauts to lunar orbit. 2 will descend to the surface using a commercial lander. Their destination: the moon's south pole. This region is unlike anything explored during Apollo. It's rugged, shadowed, and scientifically rich. Some craters have remained in permanent darkness for billions of years. Inside them, temperatures plunge to extremes, and water ice may be preserved, an invaluable resource for future exploration. Water changes everything. It can be used for drinking, for producing oxygen, for creating rocket fuel. It transforms the moon from a destination into a supply station. The astronauts will spend about a week on the surface, conducting experiments, collecting samples, and testing equipment. They will use next-generation spacesuits designed for mobility and durability in harsh environments. Then they will return to orbit, dock with Orion, and come home. But unlike Apollo, the story doesn't end there, because Artemis V follows quickly, just months later. This mission marks a shift from exploration to construction. Astronauts will return to the South Pole, this time with a rover, allowing them to travel farther than any Apollo crew. More importantly, they will begin assembling the infrastructure of a permanent lunar presence, power systems, communication arrays, surface equipment. These elements will have been delivered in advance by robotic missions. Artemis V's crew will activate and integrate them, laying the groundwork for something unprecedented, a sustained human presence on another world. NASA envisions a phased approach. First, build and test. Then, expand capabilities with semi-permanent habitats. Finally, establish continuous occupation with crews rotating regularly. The target is ambitious, a functioning lunar base by the early 2030s. To support this vision, NASA is exploring technologies that sound like science fiction. Nuclear power systems to survive the long lunar night. In situ resource utilization to extract materials from the lunar soil. Even nuclear propulsion for deep space missions beyond the moon. At the same time, political and financial pressures loom. Programs like Artemis depend on sustained funding and consistent policy support, both of which can shift with changing administrations. And there is competition. China is advancing its own lunar ambitions, with plans for a crewed landing before 2030. The timeline is tight. Any delay could alter the balance, which brings everything back to the present moment. Artemis II proved that Orion works. It demonstrated that humans can travel to lunar distances and return safely using this system. It validated critical components that future missions depend on. But it also revealed the challenges ahead. The heat shield must be improved. The landers must be proven. The schedule must hold. Every piece matters. Because this time, the goal isn't just to visit the moon, it's to stay. The capsule is back. The crew is safe. The data is being analyzed, and somewhere, another rocket is already taking shape. The question is no longer whether we can return to the moon. Now the question is whether we can build something that lasts once we get there.